Hi, everybody. Hope your week has been good
Hello.
so far. Welcome back to lesson two of AI and cybersecurity. Uh, Today, we're going to start building that foundational knowledge. And this is really going to be the stuff that everything else builds on. And it's going to get us to the point where we're able to do the capstone project. And, it's super important that you take in what we're presenting, but you're also probably going to have to do some more experimentation and research to learn about the topics. It's very nuanced and layered, but we'll present the basics and ways that you can use those today to get results. And, as you further your knowledge, you're going to be more and more adept at doing this. So don't get overwhelmed. It is a lot of stuff, but we'll get through it. Um, so, we talked about camera on. I don't care if your camera on, camera off. If you have a question, please turn your camera on. And remember to lower your hand. I think we did good last time, but I just want to kind of reiterate that. And if you got any technical difficulties, hit up Discord and Paulina can help because she knows everything. Um, And, mute discipline, I think we've done good at that too. But if there's any noise in the background, please mute. Um, so today is 2 of 16. We're just getting started. Uh, we're going to have our first assignment today if you haven't started working on that already. There was a good question in Discord, and it was about if I'm already using Jupyter Notebooks and have Python, do I need to install Anaconda? The answer is no. If you already have Jupyter Notebooks available on a system that you have access to, rock on with what you got. If you're starting from scratch, Anaconda is probably your best bet. Um, so important to note that I've redesigned this course so everything connects back into the capstone project. We're going to be able to break it up into chunks with the things we learn in the labs as we go and the information that we have. And that's going to let us get a great result at the end. I think you're going to be impressed with what you have. Um, so that's kind of for that. Uh, Today we have Jupyter Notebook set up. Should be pretty straightforward. If you got questions, hit me up in Discord. And we'll have another homework after the next lesson. And you can see kind of the structure as we go on. All right, and remember, I'm easy on homework. As long as you get it done, that's great. Okay, so today's agenda is we're going to talk about machine learning, supervised versus unsupervised. What are those things? What are some key algorithms? We're going to be using these as we go along to build the capstone project. I can show you some kind of cool examples of stuff that I have pulled together. It's been pretty amazing what you can do. And then we're going to have a brief discussion about Python libraries, everybody's favorite subject. So try and stay awake for that. Okay, so now let's dive into kind of the fundamentals and the building blocks. And we're going to start with core concepts, and everything else depends on some of this. There's going to be stuff that's going to be reiterated. We're going to sneak stuff in. If there's a question as we touch on a topic where you want more information, let me know, and we'll do our best to kind of address that in class, either that or afterwards. All right. So this is sort of the foundation we're going to build the house on. And these aren't academic concepts. You can use these in everyday cybersecurity ML projects. And hopefully, this is going to be more intuitive to you. I think the combination of using an LLM to help you write code to get results using Scikit is pretty powerful. And we're going to have some fun with this. All right. So by the end of this, you'll know what the difference between supervised and unsupervised learning is. You can identify some key algorithms. We'll be able to explain the process of training and validation. Uh, and you know which tool fits which problem. And training and validation is really where most projects fail. And we'll make sure we get it right. and then some LLM strategies, so practical skills for using AI to help with AI, which is really super powerful. It's back to my analogy earlier of, do you have a data scientist and a developer, and can you iterate quick enough to get results? We don't need those people anymore, right? We can do it ourselves. So just kind of real quickly, raise your hand if you guys have some machine learning experience. This is awesome. All right, good. This will be fun. And the rest of you that don't have machine learning experience, you're about to get some. So, and um, so, and then the big thing is, ask yourself, right, what do I want to take away from this? And it's a torrent of information, but try and pick out things. And we're going to have practical examples that kind of back these up. Okay, so we're going to spend about 15 minutes on the recap of machine learning. We'll have 20 minutes on algorithms. We've got a lot of stuff to go through, so I'm going to try to get through it best I can. I'd never stop on time. I'm sorry, but that's just how it goes. So my apologies in advance for running over, but just think about it. You're getting more for your dollar, right? And I've done this so each section builds on each other. So hopefully this all makes sense. If it doesn't, ask questions, use your LLM of choice, right? Which is a good segue. So I have always been amazed throughout my career that people ask questions that I feel they should be able to get the answers to themselves. And it used to be, I'm going to go poke through Stack Overflow. I'm going to Google it. Now you got an LLM, and you don't have to Google it and try and Frankenstein some code together from somebody's GitHub or from, Stack Overflow or someplace else, right? This LLM is gonna give you a good head start. The challenge that I've seen is that the LLM never gets it right the first time. There's always something that doesn't work quite right like it's supposed to, or you don't get the results. And the trick to this is going to be two things, right? One, if you got some coding skill, if you can hack your way through it and fix some of the stuff and then feed it back to the LLM and ask it to do something else for you, that's great. A lot of times it makes simple errors. And just being able to ask good questions and not get spaghetti code. A lot of times the LLM is going to try and give you a bunch of debug code and stuff like that. You got to say, do it without the debug code. So be specific when you're talking to it. LLMs are new. A lot of times there's a lot of resistance from businesses with respect to using them because of questions about confidentiality and things like that. But don't let that stop you from using it to get knowledge, right? You don't necessarily have to expose company information or give it specifics, right? You can ask a general question and get sent off in a direction that's going to help you get a result. So, um, you know, have an open mind with respect to LLMs. And I think especially in a cybersecurity context, there's a bunch of stuff that nobody knows how to do. I did an experiment today, and I'll show this to you. Maybe in one of the labs, but sometime soon. But basically, I wanted to go to a website that had events on it, read the events, and do analysis on them. And I was able to do that through LLM prompts. Again, I'm not a developer. There's 1,000 lines of code. It does all this amazing stuff. I kind of understand what it is, but we're going to hopefully get to the point, right, where you have the skill to be able to get those same kind of results. All right, so we're going to spend a couple minutes on each one of these. So I think the big thing is you always have to ask yourself, what problem am I trying to solve? And this is important because this is kind of like vibe coding, right? If you don't know the problem you're supposed to solve, it can take you a long time to get a result. And uh, here's a bad example. Help me with machine learning. What part of machine learning would you like to be helped with? A good example might be something like I have a network traffic logs with 50,000 records and 20 features, and includes IP addresses, packet size. I need to detect anomalous behavior, but have no labeled data. What approach should I take, right? If you give LLM specific context, it can be super helpful in giving you a result back, right? And, context matters. Uh, there's a trick that I learned. Sometimes if you ask an LLM to give you code to do something that it considers maybe nefarious or malicious, it may not return it, says I can't help you with that. But if you say, I'm a security researcher, or I'm a network administrator, and I need to figure out how many open ports there are on my network, it's a lot different than tell me how to port scan a network and get all the open ports, right? So, again, context matters. And the thing is that you need to figure out how to make it less vague. And if you can be specific and give it data and examples, you don't even have to give it data. If you can just give it features, you can have it generate a whole bunch of code for you, right? So um, some of the examples that we're doing, for instance, the Capstone project, I created a set of test data, and basically I took all the malware samples, and then another subset of the rest of the data, and used that so I could iterate through quicker and get results with the code. But you can do things like that if you have a schema that you want to feed to an LLM and you don't want to expose your corporate data. You can put dummy data in there as well. And when you get a result from code, you can run it inside using scikit and Jupyter or in your Python IDE, and you're not giving your LLM any data. So hopefully that makes sense, right? Because you can get the LLM to write you code if it knows what the schema is that it's working with. And then when you run it on your actual code, you'll get more information, or your actual data, you'll get more information about how it's going to react. So we'll show some examples of this as we're going through. But the LLM super helpful in getting results there. So let's talk a little bit about data strategy and pre-processing. And I think it's something like, Windows logs. Are they in a .avt format? Is it JSON? Do you have a CSV file? Those kinds of things. You have to be specific if you're asking an LLM to write code about what format that you want to use. I mean, for instance, if you want to do Windows log analysis, that's a pretty well-known format, and you can ask it just to write code based on a Windows .avt format. So you don't even have to actually send it any of your internal data. So think about that. Um, then, what's relevant? Log files is a favorite. Network packets, we're going to look at both of these. User behavior data, we've got some of that as well. And these are all logs that you probably have in your environment already. Maybe you have them in a Splunk sync, I don't know. But the thing is that there are all these different sources, and you look at them kind of separately because they all may have different data formats. And then we haven't talked about this. Here's a new concept. Let's talk about two things. One is features and feature engineering. So think about features. If your data has features, it has columns. So columns are features. And then there's a really grandiose term that gets thrown around called feature engineering. All feature engineering is I'm doing some operation, I'm creating another column, right? So I can do an average, I can do a sum, I could combine several columns together and create another feature out of it. It's just like you're doing it in a spreadsheet with a formula. So if you put a formula in a cell and you say, I want results from a couple different parts of my data set, and it puts it there, guess what? Congratulations, you already created a feature. So it's not as mysterious as it sounds. And it if you are not getting the results that you want, you can also talk to LM and say, hey, what should I do about feature engineering? And it may have some suggestions. I've got a couple questions in chat here. Okay. Doesn't look like anything I need to worry about. Okay. All right. So let's go and talk about, so before and after prompts, I'll provide some examples of these. I just did one. It was pretty interesting where I wanted something from, like I said, a security log website. So I'll share that chat with you in Claude and show you what the results were. Sorry, I was going to pull that in beforehand, but I got sidetracked. And then, think about the challenges you might face when you're pre-processing logs, right? Are there, fields where there's like JSON format? If you look at a Windows log, there's the features that have data, and then there's like a JSON blob. Do you need to worry about that? We'll talk about this some more as we get to malware, right? Do you need all the features? Some of them may not make sense. We'll talk about, it's called dimensionality reduction, but it's basically if I have boring features, I'm going to drop them out because they just make it harder for me to construct a model. So we're going to talk about that some more in a future session. Okay, so let's talk about model selection and architecture design. So avoid generic questions, never ask what's the best model, provide specifics, and then the context, right? Make sure that you give it some cybersecurity context if that's what you were trying to do, and you'll get better results. So if you have 1 million network events and need real-time threat detection, what do you tell the LLM, right? So you have to think those things through, and that's why we're not going anywhere. We have the domain knowledge that is going to take to get results out of LLM. And that's why this is so important, right? We need to learn how to use this to our advantage and take the knowledge that we have and, help drive things forward, right? Because it really does put the power in your hands to do things that has been hard in the past. So, code generation and implementation, this is huge, right? And if you say, I want to use Scikit, I want it in Python, I want it in Jupyter Notebook, coding style, right? Do you have error handling? A lot of times that's handy. Sometimes it's not, especially if you don't know what the errors say. And then, make sure you review any tested generated code, right? A lot of times you're going to get a result and it's not going to be what you expect. And you have to think about it a little bit to see. I'll show you an example of this later, where you look and you see the result and it's like, oh, well, I'm not seeing anything. Well, then you have to think about what is your data set. So more to come on that. All right. So now what we're going to do is talk a little bit about debugging and optimization, right? And you need to describe the symptoms clearly to the LLM, right? I want better training accuracy. I want better validation accuracy. A good example is it doesn't run. This happens a lot, right? You're gonna throw code in a Jupyter notebook and it's not gonna run. You can ask the LLM right back in the same prompt session, say, well, hey, this is the error message I'm getting. Can you fix it? And it's like, oh, I made a mistake. If you got some coding skill or you think you have some coding skill, a lot of times you can chase that stuff down yourself. I like the code that I get from my LLM, but I always make changes, especially for things like variables and hyperparameter tuning. And we'll talk about this more in the lab. And it's an iterative process. So, there's like context, right? The model takes 10 minutes to train on 100,000 samples. The model that I have been playing with for the Capstone project, sometimes it runs for 35 minutes when you run it on a full data set as opposed to a smaller data set. And the question is why, right? So you have to figure out, how do I tune hyperparameters? We talked about that a little bit. Those are like the switches. If you ever call a program and you send switches, right? That's what a hyperparameter is. So it's things that the model doesn't figure out for itself. It's where you control the model. And there's a bunch of that. And I know almost none of it, which is why I rely on an LLM to help me optimize the code and make sure that we tune the right hyperparameters. So again, this is all stuff that's going to show up in the lab. So here's a real example, right? When I first put together the demonstration notebook for the capstone project, it worked great on my smaller data set, but when I fed it the full data set, it would barf repeatedly. So I had to go through the successive process of fixing each part of it using the LLM to help me out to get to the point where it actually had something that ran and gave me results that I wanted, right? Or I think I wanted. So this is all super interesting, and we're going to kind of work through this, right? Um, so it's iterative improvements again, right? As you learn more, you're going to start doing these projects, and you're going to say, "Oh, I want to do this other thing. How can I get more results? I need to see a display instead of text. I want a CSV file as output." These are all things the LLM will help you do. Uh, I just did this today. I created a analyzer that would take replayed attacks from a log source, and it would go through and do analysis on them. And it gave me results in a JSON file. I didn't want a JSON file, so I took the JSON code, put it back in the LLM, and said, "Hey, create something that is similar to this that gives me a CSV file." And it did it in 15 seconds. I was able to paste that back into the notebook. And now, if I want a JSON file, I can get one. If I want a CSV file, I can get one. So these are all the kind of things that we're going to be working through. Use the LLM to do it. So experimental thinking, right? Here's a fancy term, an ablation study. Basically, what you're doing is you're eliminating features that don't matter in an ablation study and see if you get a better result, right? The machine learning algorithms can do this for you. It'll do feature importance, and you can say take the top N features, the top 10, top 15, and build your model based on that, and it's going to help it perform better. So for instance, I think the data set we're using for the malware capstone has 79 features, and there's probably 20 of them that actually impact the building of the model. So when we go through and talk about that, we'll talk about feature reduction and how that impacts or doesn't impact necessarily a result. So that kind of thing helps you figure out what happens if we remove this, right? What's most important, right? How do different components interact, right? Component is a feature, right? Or it's analysis based on features, right? You got to be able to do this to justify design choices. Why did you do what you're doing? Debug performance issues. I talked about that a little bit, right? We got to tune hyperparameters sometimes to get results, and then validate that the complexity is worthwhile. Maybe you don't need 20 features. Maybe you only need 15. So this is kind of, I think this is a universal truth, right? The first thing you always do is establish a baseline, right? We want to know what's normal, right? And then you can systemically eliminate the parts and you compare the performance without each one. And then you can analyze the result, right? Figure out which hurts performance the most and, if it impacts the results that you're getting. So, uh, that's super important, right? And it's basically, of all this universe of things. When I was at Google, we had a database that had 2,500 features, right? So 2,500 columns. It was telemetry data from a bunch of different sources. They wanted to stick it all in one place. And if you were looking for OS query results from MacBook users, you didn't care about the rest of it. So you could go through and eliminate, 2,420 of those columns, and you'd only have a handful, and it made your job a lot easier. And Then you got to measure impact, compare performance without the components, determine and go forward from there. And that will help you systemically improve a model. So, uh, LLMs, they help you with ML knowledge, right? You have cybersecurity knowledge, and it can help you with that as well. And it will help you suggest techniques if you ask it problems, right? And it'll help you create metrics. I'm a quantitative guy. I'm not a qualitative guy. Good doesn't do much for me, right? So you need some kind of measure. How are we moving the needle? Are we making something bigger? Are we making something smaller? That's what I think you need to focus on. And then you also need to think about, is there regulatory requirements, time constraints? But those are the key points, right? So the other thing is the critical limitations, right? LLMs can be confidently wrong, right? It's like I looked it up on Wikipedia, right? It's, well, you got to check the sources and the citations. Same thing with LLMs. LLMs lie. Code, not so much, but sources and citations, absolutely. You need to keep your eyes open for that. Again, this is why we're always going to have humans in the loop. You get the best results if you use it as a tool to help you out. Um, you know, it might suggest outdated techniques. You need to make sure. Sometimes you need to ask it to not give you results that sound like it was written by an LLM. uh, Scalability, this is a big one, right? How big is your problem? You need to make sure that you're talking about that, because that can make a big difference in what it can suggest. And LLMs don't think, LLMs don't reason, LLMs are a giant F statement. There's no replacement for you, the human in the loop, right? The knowledge that you possess. It gives you the ability to ask questions. It gives you the ability to evaluate results. It gives you results, the ability to make code run. And without any of that, right, LLM is just going to spit out a bunch of garbage. It's a tool. Like I said, it's a supercharged Google search and all the other stuff combined together. It knows all the stuff that's out there already and can give you results. But again, it doesn't always get it right the first time. So don't over rely on LLM output. Read it, try and understand it. A lot of times code is hard to understand, but if you look at it, if you take each section and say, I want you to describe what this section does, it will help you out, right? I have lots of examples that I'm going to share as we go along about where LLM got something wrong and I had to work through it. So I'll share the prompts with you about how I got the results for some of these notebooks. I've got this stuff all saved up. We'll talk about it during labs. And then, the question is, how do you validate LLM suggestions? I know this is like a lot, especially when we're talking about LLMs generating code and putting it in notebooks and things like that. You should get familiar with something like VS Code, right? Because if you can take your Python code, throw it in VS Code, it's going to help you debug the code and it's going to be easier to format it and stuff like that. I am by no means a VS Code wizard. I use it at Google. I use it now. But I think it's one of those universal skills, right? You should take some time to try and learn it, especially if you're going to be an AI wrangler trying to sling some Python code. And I can show you some examples of LLM failures. I had a good one today. It was kind of funny, but we'll see how much time we have and see if I can share that. So this is an example. We were talking about ablation studies. This is a feature reduction, top 15 feature importance of the data set we're going to be using for malware, our malware detector. But this is the kind of stuff that you're going to see. So instead of 79 features, you've got the top 15. And if we can train the model on this, it's going to give us a better result. Okay, deep breath. All right. So let's take a quick second and do a recap of what machine learning is from the last class, right? I think the important thing is that this helps you do learning from data and uses pattern identification. What almost everybody has done is you've done things in spreadsheets And a lot of times you're looking at one or two columns, which equates to one or two features. And you're trying to get a result from that, but you can't forecast things based on the contents of all the other features. It's just too hard. If you're a whiz with Excel, maybe you can do some of this, but machine learning algorithms help you do that. And it can also predict in the future if something is going out of spec and you don't have to do this analysis manually. I was having a discussion with somebody the other day and we were talking about this. And this is back to the old example. If you've ever been an incident responder or a threat hunter, you know that there's a lot of stuff that you do manually and it's repetitive and it doesn't really require that much skill. If I need to go take a image of a drive or I need to do some forensic data collection and things like that, right? That's all done manually. But the thing is if we're using machine learning, we can detect patterns and we can help present those results back to the person, right? So this is super important, right? And the connection is really to cybersecurity. We're drowning in data, right? The existing model of security management and response as a tiered effort is, I think, going to go by the wayside. And we're going to be able to leverage what we have learned through machine learning to help find patterns. And then we can help build software or detections that are going to help resolve some of these things. We can automate runbooks. We can automate incident response. And a lot of the tier one, tier two stuff is that is repetitive and dull and people hate doing, hopefully gets automated out and we can use those resources and leverage them to do something with a higher purpose. So, machine learning is sort of the basis of the larger AI ecosystem. And the key difference from traditional programming is that you're learning from the data. You're not trying to come up with an algorithm and get a result, right? It's like if you do a SQL query, you never know what you're going to get, especially if you're doing feature engineering and stuff like that. It's kind of a crapshoot, right? So if you can use a machine learning algorithm, it can analyze the data for you and it can help show you patterns that you may not be obvious to you just because of the complexity and the size of the data, right? And there are patterns that humans might miss. And we have examples of those to talk through. It improves with data. More data generally means better performance. We'll see that with a small data set and one of the examples, and then we'll show what the result is with the larger data set, and you can really see the difference. And then here's an interesting takeaway that you guys need to consider from this, right? Traditionally, humans write security rules, and in the past, right, we've based things on these atomic detections, right? Things that it's our best guess back to the IDS example of what is malicious and what isn't malicious. Now we have the ability to see things that are not normal and identify those. And that's how we find anomalies. And anomalies, a lot of times, equate to, adversarial activity. And we have more to talk about with that as well as we go. And so, classifying spam, right? We have a little example. We can talk through that. Intrusion detection. We have a lab we'll go through talking about identifying abnormal network behavior, malware, recognizing malicious code patterns. And this is all done using machine learning techniques, right? And if you take machine learning techniques and you combine it with automation through agentic AI, right, that's how you automate things. And a lot of this is kind of in the future, but if you are able to do the machine learning techniques, you can layer the other stuff on top of it. So machine learning is just not statistics. It's not magic. It needs good data. And models need maintenance and updates. And these are all the kinds of things that we're going to be talking through. Okay. So what is an anomaly, right? If you look at statistics, It's essentially anything that's more than 3 standard deviations from the mean, right? You consider this an anomaly. So, so in a microcosm, if you're looking at just one feature or one composite statistic, this is kind of interesting. But how do you scale this, right? How do you look at what's an anomaly in the context of a larger set of data? And this is what machine learning is going to help us do, right? Um, most data follows normal distribution. It doesn't, a lot of it times it doesn't either. That's why median is a crappy statistical evaluation. And in my opinion, mean is not great. Median is better, right? Because half or more and half or less. That tells you whether the data is skewed, is it stacked one way or the other. You can also talk about there's kurtosis, which your data has a funky shape. It's not traditionally a bell curve. You don't have to worry about that so much with machine learning. Or if you're using machine learning, that might actually help you out because maybe you're able to identify anomalies through the shape of the data, right? Um, so we talked about the 2 or 3 standard deviations from the mean, right? That's probably, I don't know, high school, early college math. It's been a long time, right? Uh, how do you figure out what a standard deviation? That's called a z-score. And when you have the z-score, it is the different components are x is the individual data point that you're examining. The thing that looks like a funky U is called mu, is the mean of your data set. The other element, the little circle with the tail on top is sigma. That's the standard deviation in your data set. And Z is the Z-score, standardized score. And what that tells us is how many standard deviations away from average is this data point. So every data point has it. You can calculate a Z-score, and that'll tell you kind of where it lies, right? If it's 0, it's the average. If it's 1, it's 1 standard deviation above. -1, you're going to the right. It's 1 standard deviation below. And then 2.5, same kind of thing, right? So you could build a threshold and say if Z is greater than 2.5 to 3, flag it as an anomaly. And that's in a very basic sense how you can think about anomaly detection, right? So if you look at the bell curve, where are the anomalies, right? Those are those red areas. If the mean is 100, standard deviation is 15, is 145 an anomaly, right? That's 3 standard deviations. So maybe, right? Um, an example of an anomaly would be network traffic that's 3 times the normal volume, right? That would stick out like a sore thumb, right? Because it's beyond that 3 standard deviations from the mean, right? So the advantage of this is it's simple, it's fast, it's easy to explain. It works well for single variable, normally distributed data, but how often do you run into that in security? Sometimes you do, sometimes you don't, right? Network traffic doesn't normally follow a normal distribution. It's not the same level all the time. It's bursty, right? It's a single variable, right? How do you talk about something where you have dimensionality? You want to understand the relationship between different features, right? Bell curve doesn't necessarily help you out there. And that's what we call the curse of dimensionality, right? This works good for one kind of homogeneous set of data, but it doesn't really look at the entire range of data and give you a result. So this would be good for something basic like CPU monitoring, login frequency, but it wouldn't be very good for complex patterns or user behavior analysis. So what do we do with machine learning, right? We have things like multivariate methods, right? Ooh, that sounds pretty fancy. And real data is messy, it's complex. Machine learning multivariate capability can handle many features simultaneously, right? We're going to see this as we go on. So it can handle 15 features, and it does sort of some kind of cosmic bell curve and gives you results. And it can also address non-linear relationships, complex patterns, especially things like malware. There's a lot of interesting stuff there that we'll talk through, and it's super helpful there. So what are multivariate methods? We've got isolation forest, right? It isolates anomalies by partitioning data. So anomalies stick out like a sore thumb. In isolation forest, we'll see this. So you have clusters that are separate kind of from that mean, and it's going to be easy to visualize. We have local outlier factor. It compares the density of points. Um, so anomalies have fewer neighbors. There's less of them. That's less dense. Things like user behavior analysis. If I have a login from a known usual address in the US and I have a few logins from outside the US, that would be one of those things that would stick out. One class SVM, support vector machine, it creates a boundary around normal data, and then it says anything that is outside the boundary with a certain precision is considered an anomaly. And this is useful for like baseline system behavior. And we can talk about neural network approaches, right? This is like NLP. We have autoencoders, right, which will reconstruct normal data, but they don't do well with anomalies. And if it can't recreate it, it's probably anomalous. And that's sort of the basic theory, is if it doesn't fall into the realm of what it can manufacture, it's going to flag it. So things like malware detection and network monitoring. Um, Variational autoencoders, they learn probability distributions of normal data, and they have a more robust uncertainty estimation. Uncertainty is, I don't know if it is or it isn't. And then these are all kind of things that we're going to dig into a little bit more as we go forward. So here's a comparison of statistics and machine learning, right? Uh, Traditionally, statistics are for a single variable, a nice bell curve. Machine learning is multiple variables, like login frequency versus a full user behavior profile. Interpretability is always a struggle when you're trying to relate concepts to people that may not have a deep understanding of machine learning, right? Statistics are easy to explain. We're talking about one variable. Machine learning, it's not a black box, it's statistics on steroids. It's harder to explain the decisions. And things like compliance and forensics, they need interpretability. And if you can't explain it, again, it's going to be hard to get people to buy it. As far as cost, computation statistics are fast or simple. Machine learning is more complex, requires training. There's more steps to it. You can't just plunk data in a spreadsheet and show a distribution and a pivot chart, that kind of stuff. And you have to think about this too. If you're thinking about some kind of real-time detection, how much computational power do you need to do the analysis? Can you keep up with the level of logs? Is this something maybe you need to do offline as opposed to real time? Training data. For statistics, you just need mean and standard deviation. ML, you need a large representative data set. And the big challenge in cybersecurity is most of the stuff we have is not labeled, right? So how do you know what's an anomaly? How do you know what's an attack? This is where your domain knowledge comes in. Where you can help look for other patterns. This is the supervised versus unsupervised challenge. If you're unsupervised, you're just kind of fishing, looking for anomalies. Whereas with supervised learning, you have labeled data and you can train a model, and it's going to go a lot quicker. We're going to cover both these techniques in labs and stuff as we go. Statistics, again, sensors, well understood processes. Machine learning is, things like fraud detection, text analysis, network behavior. And, you have to make that decision, right? do you need interpretability or do you need accuracy, right? So that helps you decide what you should use. Okay, so what we're going to talk, you're going to see a lot of our modern hybrid approaches, right? We're going to have ensemble methods where we combine multiple techniques for better results. And we'll use statistical ML methods at Vote. And this is like more robust threat detection. We can talk through feature engineering, right? We can use statistical measures as ML inputs, right? You can do calculations and weights and things like that of different features and create new features. This will help model training sometimes. You know, you can, again, use your LLM to help you suggest you know, features, those kinds of things to help get better results. Threshold learning, right? You can use ML to set statistical thresholds, right? So dynamic anomaly detection, right? You aren't stuck with one model, you can have changes. You know, contextual anomalies. So ML helps you identify the context, statistic detect deviations. That's like a two-dimensional versus three-dimensional analysis. And, you know, it would be like normal behavior data and, you know, things like time-based and user-based contexts. We have some examples of this where, you know, something happens at a certain time. Is that normal or isn't it normal, right? And it's super useful to have things on a timestamp. And, you know, so just an example from a workflow would be, right, you have raw data, you do statistical pre-processing, feature engineering, you create an ML model, and then you have an anomaly score. So each step adds value, you can get results from each one. And then you need to do this to make ML more interpretable and make sure that people are on board and that they will adopt the applications. So this is a big change for a lot of people. A lot of people don't, when you say AI, they get scared. They think, you know, I'm putting, you know, all our company code into an ML model and an LLM on the internet, and it's all going to be out there for everybody. That's not what we're talking about. We're talking about, this is data science, right? These are things data scientists have done traditionally in the past, but it's hard because unless you're a data scientist with a background in cybersecurity, it's hard to put these two things together. Okay, so let's keep rolling here. Let's talk about supervised learning, right? This is where we learn from data that has been labeled. This is an example from scikit-learn, right? We'll be working with scikit in our first lab. So it has a correct answer. It's like, is it malware? Isn't it malware? Is it anomalous? Isn't it anomalous? Is this attack attempt, right? So there will be a feature that has a label in it. So this is like learning with a teacher. You have, and it's simpler to train a model because you're able to tell, well, this is an example of what's good and what's bad, as opposed to, well, these are things that are anomalous, so you need to go check it out. So another concept we want to talk through is classification, right? This is predicting categories. So is it spam? Isn't it spam? Is it malware? Is it benign? Is it threat? No threat. And this is important to us because most security problems are related to classification. Regression is predicting continuous numerical values, right? House prices, temperatures, risk scores, uh, you know, done regression analysis and found advanced persistent threats based on search volume. It was initially a technique that our red team used, and we actually were able to use that to find you know, APT actors that have foothold in the environment. So that was pretty cool. And you know, one thing that is kind of cool with this, if you look at this visual, is this shows you kind of where the decision boundaries are. right? So you see those differences between the different colors. Those are the decision boundaries. And that helps you understand kind of which of these classifiers work best just by getting this visual interpretation. And it's pretty cool because it's something that is easy to explain to someone, and it also provides a good guide for you as the person who's putting this together as to what's going on. So if you look at it, right, each one of these algorithms creates different boundaries. There's some clutter in based on the algorithm in some of these, and that is how you as a person doing the analysis can choose the correct algorithm to build a detection perhaps. And also it is useful to explain it to somebody when you're trying to tell them what you're doing. uh, so real quick, right, is predicting spam a classification or a regression, right? So spam or not spam is classification. How much spam is regression, right? And we have lots of classification problems in cybersecurity, right? Is it malicious? Isn't it malicious? Is it malware? Not malware? Is it a vulnerability? Not? And those are all things I think machine learning can help us do a better job at, right? Get rid of false positives, focus on the most important things. If I have 20,000 threats that I found in one log sample, what are the most important ones that I need to go after, right? That's what we're going to try and work through. So, uh, common examples are classifications like malware detection, intrusion detection, phishing, regressions, risk scoring, resource utilization, attack severity, and we'll have some more examples of these as we go. So unsupervised learning, this is the cool stuff, right? It learns from data that has no labels, right? There's no correct answers, right? It'll find those same sort of clusters and help do the classification, but it'll do it by looking at the data, right? So it's good for finding patterns without knowing what to look for. What hidden structures exist in the data? Clustering is grouping similar data points together. So an example would be like customer segments, attack patterns, user behavior groups. The relevance is that we're discovering new threat patterns, right? That this is something that we didn't know about. We couldn't say, go find it, but we look at the data and things get clustered together, right? How many logins are happening after normal business hours, and where are they coming from, right? That's a question maybe you could put to unsupervised them. You know, and discover new threat patterns. Dimensionality reduction, I mentioned this, right? You got to simplify complex data, but you need to keep the important information. Like reducing 1,000 features to 10 key ones. And this helps you make complex network data manageable, right? You think about all the different fields that you can have in Splunk and things like that. What is really important in all that, right? Do you go through each field? Do you know which each one is? Sometimes you do. I know I used to do that. And if you don't have the time, if you're trying to get a result, right, we can use machine learning techniques to do dimensionality reduction. Sorry. You can visually look at clustering and it will pose some questions, right? You look at some of these different uh, uh, clusters that are here and the different methods that they're using, right? What are those things, right? We'll talk through this. This is an example from Scikit, but these are all the kinds of things that you can get as far as a result when you're using machine learning techniques, right? So if you have network logs and you don't have labels, what could you discover? We have some examples that we'll show in labs, right, where we have unlabeled data and we're able to get results from it, right? Clustering, how could that help in cybersecurity, right? What's normal and what's not normal? If I have a cluster that has a few elements in it in a larger data set, maybe I want to go and do an investigation of this, right? So, these are all great things. Anomaly detection, right? We're looking for unusual patterns without labeled examples. Okay, so we're going to talk about a comparison quickly here. So supervised, again, gives you examples with, needs examples with correct answers, right? So you need to be able to feed a supervised machine learning training set that has labels, right? It is malware, it's benign, it's an attack, it's not. We'll see more of this in labs. So supervised needs more preparation, right? Supervised makes predictions on new data. Unsupervised understands the structure of existing data. And the decision factor is what are you trying to accomplish? It's like if you have a large set of data where you already know what the correct answers are and you want to be able to scale through it, probably supervised learning, right? If you have a set of, like, say, network logs or traffic logs that you want to look for patterns in, you don't know, maybe you don't know the question you're asking, you just want to see kind of what's weird out there, unsupervised would definitely be your selection, right? So supervised gives you clear right and wrong feedback, right? You have two clusters, one is and one isn't. Unsupervised, it's harder to evaluate, right? What does it all mean? You sort of have to gaze into the crystal ball and figure out what's going on. Again, can't replace a human in the loop here. This machine learning and AI isn't going to train itself, so they're going to need people like us, right? And uh, practically, how do you know if the clustering is good? Sometimes it's experience, but you can use your LLM, right? Use LLM at your disposal to help you get some answers with respect to some of this. So, common things you do is supervised is classification and regression. Unsupervised is clustering and dimensionality reduction. And if you have ensemble techniques, you can use them together, right? So with respect to, the teacher element is supervised, like having a teacher with answer, and unsupervised is research, and it's guided versus exploratory, right? I spend a lot of time in all my jobs doing exploratory stuff, right? So the answer isn't obvious. I have a hunch and I want to try and get more data and I want to try and come to a conclusion. So I'm a lot of times using unsupervised techniques. So if you want to detect a new type of malware, right, that would probably be unsupervised, right? 10,000 labeled phishing emails would be supervised. You can have labeled data and find new patterns. We'll show an example of this in our malware detector, right? So there's a lot of different elements to this. Okay. I told you we were going to run over. All right. So briefly, we're going to talk about algorithms. This is intuitive. This isn't math, right? Don't get too freaked out about this. And it's a practical understanding. We're going to touch on some of these. I encourage you to do more research, right? This is all super fascinating stuff to me, but I'm a nerd, so sorry.
Steve, before we go on, do you mind if we ask a question on the last topic?
Yeah, go ahead.
So in supervisors, unsupervised, like if we have an example where, let's say we get a bunch of text, like let's say we're collecting challenges from a set of people, right? And they write in prose, like, text, here are all my challenges with whatever subject. And then you want to classify each of those, right? And say, okay, from this text, like let's say some of their challenges could be budget related, or it could be vendor related, or it could be whatever it is. What would be the best approach for something like that? Would you like go through and then like manually label it in order to do supervised learning and then provide like in like a subset and then provide the rest of the data set to see
We
if it
actually,
like was it
we
correctly
actually have
or
an example of you're foreshadowing some lab stuff. So I would use an NLP technique, right? I would use a neuro linguistic toolkit, NLTK, and you could do a word cloud. You can look at uh, the frequency of terms. You can look at the relationship of terms to different users and those kinds of things. So there's some techniques we'll explore in that. The example we're using is actually a Windows log set where somebody's running Mimikatz, but it's a similar kind of thing because we're analyzing the contents of the logs, the text, and looking for things like that. So did that answer your question?
yeah, so could you repeat the answer? You said it was Windows log set, Mimikatz, and the what was the other?
It was a Windows log set. We were looking for uh a user that was running Mimikatz. So I could relate a specific user that ran Mimikatz and the frequency of it. So that's all done with NLP techniques and the NLTK. And that's one of our I have an example for that later on that we'll dive into. But there are techniques for that, and we can dive into that a little bit more. But I understand what you're asking. And yes, you can do it. It's not, I would say it's unsupervised. NLTK is neural network technique, and we'll show an example of that, and you'll be able to play around with it.
Okay, thanks.
Cool. Swayam, you got a question?
Yeah, it's like a general question. Like, from your knowledge, is there more supervised or unsupervised learning in like the work field?
I think people do supervise because it's easier,
Okay.
but I think the interesting stuff you find is unsupervised. So if you're on a quest, maybe you don't know, right? You know, what does normal login activity look like in my network, right? What are the
Yeah.
types of logins? When do they occur? Those kinds of things. That would be something where you could do unsupervised learning. Like
Right.
show me the clusters of logins. So does that make sense?
Yeah, that makes sense.
All right,
All right.
cool.
Thank you.
Andrew? Yeah, you bet. Andrew?
Hey, I just had a quick question about like integrating with like Seam, like Splunk and other resources that are centralized so that you can use an internal model to basically set up both supervised and unsupervised.
Yep. Yeah, that's the benefit of a platform is the platform has models already, and if you understand what they're used for and how to tune the hyperparameters to get results with them, it's super helpful. But I would say a takeaway from this course would be okay, now instead of it just being a black box where I run it and see the result, I can dig into it a little bit more and maybe I can tune it to get a better result for me.
But for
So
somebody like me, if I'm a little bit more focused on unsupervised, or pardon me, hyper-focused functions, got it. Thank you, sir.
yeah, okay. All right, Tutu.
Yes, hi. Can you explain what the unsupervised or the labeled data will look like? So, what makes it unlabeled and what makes it labeled? Um,
That
is
is a
it like,
great question. I'm glad you asked that.
yeah,
So
is it like raw data without it being
I I don't have an example handy. I will try and explain it. It's like if you have a spreadsheet and one of the columns is malware and it says malware or benign on the related to the specific log entry, that is a label. So for instance, if you had a bunch of um, uh, email samples and they were labeled spam or not spam, that column that labels them, that's what we talk about when we say it's labeled.
Oh, like a file, a folder that's labeled.
Well, yeah, it's like if you have a spreadsheet and it has a column and it identifies the row as, you know, good or bad or malware or not malware, that is a label.
So where does is this where the where does the SQL come into play here? Like if you're dealing with raw data, is it when you have the SQL to categorize your data in a spreadsheet or?
Stuff gets labeled, it either gets labeled by people or it gets labeled by programs. You know, you can have machine learning and it can do labeling, but a lot of times samples are labeled. You know, for instance, we have malware data that came from VirusTotal. So VirusTotal went through and identified malware and it labeled each one of the samples, right? So we know with the data we have for the capstone, it's been labeled by VirusTotal. It could come from somewhere else, right? It could come from a different data set. It could come from you know, a different website. But at the end of the day, right, it is you receive the data and you already know what each entry in the data is, whether it is one thing or another. It could be 15 different things, right? And then we can talk about clustering. We'll talk about this some more, but it's basically the label that's associated. Does that make sense?
Yes, thank you.
Yeah, you bet. Andrew?
Hey Tutu, in everybody, I just wanted to raise like an example of labeling data, that's specific for cybersecurity. So if you're talking about like um common vulnerability enumeration that's like provided by NIST or common weakness enumeration, OSWAP top 10, all of those things are labeled specifically for cybersecurity, right? So we can all be on the same page and we can all understand those vulnerabilities or those weaknesses, whatever, and report kind of in the same way.
Yep. Great example. Thank you for that, Andrew.
Thank you.
Yep.
Okay. All right. Diving deeper, hold your nose. Okay, so we're going to touch on this briefly. Linear regression, supervised learning. A lot of times, supervised learning, you'll see it, the decision curve is straight. It's not an S curve, right? So it it is fairly simple. You know, it has a continuous input value and continuous output value, right? It's a best fit. Trying to think of a good example, right? If you have ever tried to do like a detection, right? You have to have a threshold in a detection. That's really kind of linear regression you're trying to fit. You're drawing a straight line best as you can through a bunch of points, and that's kind of giving you the bit answer, right? And then it uses the line. If it's on one side of the line, it's in. If it's on the other side of the line, it's out. If you look at that example to the right, that shows you kind of inliers and outliers and where the decision boundary is for the linear regression. And you can see that that cluster of yellow dots, right? There's less of them. And that's, you know, usually indicative of an anomaly. So you could see that with that blue line, it projects what the decision boundary would be of the linear regression algorithm. And it would probably have some things that would be in if you would have just taken the average based on the most common features, but but it tilts a little bit. So what we're getting there is, you know, our recall is different, right? So precision is how many times we get it right. Recall is how many times we get it wrong, and you can see that there's a balance. So, you know, things that this is good for is like baseline predictions, like CPU usage, resource forecasting, bandwidth needs, trend analysis, attack frequency over time. So it's one thing. It's like if you look at a bunch of scatter points, like look at that middle example there, a test set, a linear regression, right? You sort of have to imagine where that line is, right? That's sort of an intuition check as you look at it and say, oh, does that make sense? It's a little bit harder in the training set. Um, and then, so an example would be, how long does a security scan take? Right? You have a bunch of data with that, right? What's the average? And if you use linear regression, you could say, oh, I want to get a notification when a scan is taking longer than it should. And you could do that. So these are simple, they're fast, they're easy to interpret the results, they're a good baseline. But some of the limitations are that the assumption is the relationship is linear. Outliers mess it up. You can see kind of in the right-hand example there with the blue line, the outliers pull it over, and that's going to make our recall a little bit less precise, right? Because we're going to get more answers wrong than we would if we tilted the curve the other way. And it might not capture complex patterns, right? If you could imagine in that left-hand example, what if there's more dots, right? It's a little bit harder for it to figure out. Okay. So this is a fun one, logistic regression. This gets used a lot, like the general logistics equation, if you've ever heard of that before. So instead of a straight line, this uses an S-curve, right? It gives the probability of belonging to each class. So it's not always, it's not a straight line. It's not just it's in or it's out, right? There's a probability that something belongs to these different classes, right? And it predicts categories, not continuous values. And you can see kind of by those different clusters where it draws what they call these hyperplanes. And the hyperplanes are sort of where it decides if the cluster's in one area or another, right? Which class does it belong to? Hyperplanes, again, are those dotted lines. Those are the decision boundaries that separate the classes. Think about what we were just talking about in the previous slide, right? We had one decision boundary, that blue line, right? In this, we have multiple. So you can see how this addresses where we have many different clusters of data. It's not just general. We can draw one line through it. It helps you interpret the probability. It can show you the confidence in predictions, right? This is sort of the decision boundary, right? How like F1 score, how far away from the decision boundary is good and is bad. If you have a broad decision boundary, can make you more susceptible maybe to having problems with precision and recall, right? Somebody might be able to figure that out and fake out your algorithm. We'll see that in one of the examples in one of the labs. And that's super important. And it can handle more than two categories, right? So it's not just you're in or you're out. This helps where you have a complex data set. So an example would be, malware, is it benign? Is it a threat or not a threat? How confident are you in this classification, right? The closer you get to those hyperplanes or those decision boundaries, right, the less confident we are. Multiple classes of problems, right? What are the different types of attacks? If you show the clusters of the we have a DDoS, we have password spraying, we have port scanning, those kinds of things. You can use this technique to break those up. So the key advantages that provides you an estimate of probability, right, is the sample is in this class with a certain percentage. It doesn't make any assumptions about feature distribution. This is based on what it learns from the data. It's less sensitive to outliers. You can see that because you have all these different clusters and hyperplanes, and it's fast and efficient, right? So logistic regression is pretty fast. And how it relates to what we're talking about with cybersecurity is you can adjust how sensitive the system is, right? How close are we to that hyperplane, that decision boundary, right? Are we giving things more leeway? We can model that and see how effective our detections are. Confidence, right? You know when the model is uncertain. If you've got something that has low confidence, right? Is it something maybe you need to look into more? And it's interpretability, and you can explain why something is classified, right? You can show a visual example of that. Okay, so decision trees, these are fun, right? It's supervised learning, it's classification and regression. It's like a flow chart of yes, no questions, right? You're asking 20 questions and you ask strategic questions to narrow down to the answer, and it's rule-based, right? You have clear if then rules. You have clear decision boundaries, right? It creates the rectangular regions. Feature pairs, right? The split is based on a single feature, and interpretable regions, and you can explain exactly why a decision was made. And we're going to talk about this. This is in scikit-learn. It's about flower classification, and it's really a super simple data set, but you can do a lot of cool stuff with it, right? You know, an example for something we would use this for in security is that you could create interpretable security rules. Remember, we want to make sure that everything is explainable. We can do forensic analysis. Why exactly was an alert triggered, right? We'll have this ability to do that using decision trees, right? And it's like a flow chart. And it's easy to audit and explain the decisions, right? So I put like this is super simple, right? This is probably the simplest thing. But basically I put together a decision tree, right? And my decision tree is the world's worst spam detector that I could come up with. And you know, basically I said, okay, so here's the few things that we're going to look for, and this is how we're going to help decide if something is spam, right? If it contains free, we say, yeah, it's 85% spam. No, we ask another question. Does the subject have exclamation points or dollar signs in it? Yes, we're 92% sure it's spam, right? No, is it from somebody we know? Yes, so it's not spam, right? Capital words and on from here, right? This is really the essence of a decision tree. It's like a flow chart, and we're going through and asking these questions. Okay. All right, random forests. These are fun, right? Another type of supervised learning. This builds on decision tree concepts. It builds multiple decision trees, and it votes by committee. Have you ever done like a Monte Carlo simulation where you go through and everybody has a vote and they put things up, right? It's similar to that, right? The majority wins. It's an ensemble method, and it combines multiple models for better performance. You know, you can have multiple boundaries, right? See how different trees create different boundaries, right? Decision tree, random forest, extra trees, AdaBoost. These are all algorithms that we're talking about here at the top, right? We will be playing with some of these. The parameter panel show the many configuration options. Remember when I mentioned hyperparameters, right? These are hyperparameters, right? A lot of these are tunable as you use the algorithms, right? And they help give you different results. Again, your LLM can help you tune your hyperparameters. And the combined result of an ensemble effect is definitely more robust. Key advantages: reduces overfitting, right? Because that's basically you think about it too deeply, or the algorithm does. They work pretty well out of the box. Feature importance, remember that when we talked about that earlier. Tell us which features matter most. A lot of times it's which have the most variation, right? A lot of times it picks features that have the most variation as the strongest ones. And it handles missing data, right? Built-in mechanisms for missing values. So that's handy, so we don't have to do a lot of stuff with preprocessing. So you know, the analogy is that 100 experts are better than one. And again, I alluded to hyperparameters. Sorry, I got excited about hyperparameters. This is where you can make things run better and faster. and get better results. So these are things that you have control over and you play with. And this is all stuff that we're going to cover some more as we get in here, right? So an application we'll be doing, part of our malware detection is we do use tree structure. So it's a robust classification with many features. Intrusion detection, we have a DDoS example, I think, where we're going to use some of this. And as far as feature analysis, it'll identify the most important security indicators, right? They're highly accurate, it's robust, isn't as sensitive to outliers of noise. You can train the trees simultaneously, and it gives you a built-in feature ranking. Things you got to be concerned about is it's less interpretable. It's harder to explain it than a single tree. They're more complex. It's a lot of parameters to tune. And memory usage, I have run my machine out of memory more times than I can think, trying to run these with the hyperparameters tuned wrong. So we'll talk about some strategies for this. But again, this is an area where your LLM is going to help you. All right, so let's talk about clustering, right? Exciting stuff here. These are grouping similar things. So it's like sorting mixed toys into piles. If you had a giant bin of different colored ducks and you wanted to sort them, that's kind of k-means exercise, right? Then you can specify clusters. How many clusters do you want? A lot of times you have to do inspection to do this. Maybe you know something about the data, and maybe there's a feature that you can key on to cluster, but you can specify how many groups you want. And then there's this concept of a centroid, right? That's the center of the cluster. Those X's there are kind of the centroids. And maybe it's more the median than the mean, but it is in that cluster, it's the center-ish, at least according to the algorithm. And this is obtuse. Voronoi regions, each color region belongs to one cluster, right? So each one of those different colors is a Voronoi region. This is a iterative process that starts with random centers and then improves. What it tries to do is it says, well, I think these are the centers based on the number of clusters that you told me. And this is sort of, I guess gravity is an example, right? Based on the number of things around this point that you gave me, I'm going to build a cluster, and it adjusts based on and basically what it does is it assigns a point to the nearest center, moves them around until it gets a better result, and it just repeats that until the center stops moving. So it's like, how would you sort toys if you had to make exactly 3 piles, right? How do you decide how many piles, right? Do I do it by color? Do I do it by size? Maybe I do it by size and color. I can have more clusters based on that. So it's like user behavior data. What groups might you have? People that are surfing the web, people that are going to Netflix, that kind of stuff. And applications are that you can segment users, you can group them, attack classifications, network segmentation, anomaly detection, right? These are all things that you can use clustering for. We've seen that everything that we've seen so far, there have been clusters associated with it. It's a key concept of machine learning, right? The cool thing about this is it's easy to understand. It works with large data sets, and it always finds some solution. You need to specify the number of clusters, unfortunately, so you kind of have to take a guess. It works best with kind of round, similar sized groups. And if you give it different starting points, you might get different results. So, again, LLM can help you here. Okay, so different phases here. We have a multi-stage training process. And what we're going to do is talk about how you approach a machine learning exercise, right? We do data preparation and splitting, right? You divide your data set into training, validation, and test sets. And you can specify this when you do parameter tunings. We'll cover this in more detail later. The training set teaches the model. The validation set helps you tune the hyperparameters and prevent overfitting, which means I rat hole on one particular facet of my analysis. And the test set gives you a performance evaluation. The model architecture selection, right, is what problem are we trying to solve? Data characteristics, is the size, complexity, feature types, right? Is it numeric features? Is it date, time? Is it text? That kind of stuff. And algorithms, right? Do we want a linear algorithm? Do we want tree-based? Do we want neural networks, right? Or we look at a text? Do we want ensembles, right? So this is important, right? Is you have to try and decide. We'll talk about how you can use LM and code to make you decide. Feature engineering and selection, right? You transform the data. You create new features, handle missing values, right? More features always isn't better, right? You can go through and say, I don't need names. I don't need things that I can't do machine learning on, and you can cut those out. We'll talk about that. And why wouldn't you use all the data from training, right? How would you know what results you're getting with a test, right? How much data do you have? Do you have 1 million records, right? What are some of your considerations there? And then feature engineering's, right? You can help the model along if you know something about the data, and you can create a feature that helps it learn, right? So, think about like attacks are rare compared to normal traffic. A lot of times they go under the radar. There's temporal patterns, time series. Some features might be sensitive, right? Maybe you don't want command line to be a feature in there. And then again, feature engineering, domain knowledge is crucial. Andrew?
Hey, quick question when it comes to feature engineering and like selection. Will we have any opportunity to get your insights on actually if we need to move beyond our local workstations and we want to establish something from an organizational perspective within the cloud, like how we model that and how we like scale that? Whether it needs to be, you know what I mean, like an EC2 instance or some sort of 15-minute, quick acting Lambda or from the
Yeah, this is kind of a lot of stuff that we do as cybersecurity practitioners are science projects, and then you need to think about the size of the data, right? Do you have petabytes of data that you need to go through and those kinds of things? And that's an application scaling decision that you could ask your LLM, but I think DevOps would probably be a good place to go through that next, right? Because really what we're doing is we're doing like a proof of concept, something small scale. And if we want to operationalize it, if we think we get the good results, we need to have that next level of discussion. Like here's my science project. Here's the requirements. Here's what I'm trying to do. Where do we need to put that?
Got it. Thank you, sir. I
Yeah, you
appreciate
bet. Yeah. Okay. Let's talk about training. We are so over time. I'm so sorry. So what do you do here, right? The key things are hyperparameter tuning. We'll talk about this. These are the switches, not learn from the data. LLM can really help you here. And validation data helps you test different hyperparameters, right? From the training data what the result should be, right? The test data makes sure that your algorithm works, and then you can tune your hyperparameters using the validation data, right? To see if you can get results that match your results from the training data. Model training and optimization is iterative. And you have to be able to adjust parameters, right? And eventually, we're going to show some methods here. There's this thing called the elbow method that helps you determine when making changes to like clustering and hyperparameters doesn't make any sense. anymore. And it's like the law of diminishing returns, right? Validation of performance monitoring, right? We got to make sure that we continually evaluate, especially as we scale. And then, you can overfit, which means you can overtrain, right? So your training data set size, you have to think is, if I feed it too much data and train it, am I teaching it, am I reducing its ability to provide me a result? We talked about hyper parameter tuning. We'll cover that some more in labs in the future. How do you know when to stop training, right? That's what I was talking about. Elbow method will show that. And, cybersecurity, right? Precision matters more than recall for some security tasks, right? We want to make sure that we don't miss anything. And it's okay maybe if we get some false positives, because we can address those. We'd rather have a false positive than a false negative. And if you're going to do training, it has to be fast. I think that goes back to Andrew's question, like, when do I put this in the cloud, right? And then concept drift, you have to continue revisiting the model because attacks are going to change over time, right? All right, and then we have model selection and finalization. This is where you wrap up the training process. And you have to make sure you select the right model. You have to compare the different algorithms and hyperparameters and features. Where did you get the best performance? We'll show examples of this, like the difference between in PCA with different algorithms, primary component analysis. How accurate am I making predictions? We're going to look through that. A lot of times, this is an iterative process. You have to go back a lot, right? And it's continuous performance improvement, right? You always need to be looking at your code, figuring out how it works. Are the results believable, right? Do you understand enough about it? You can't, if you don't understand what you're feeding it to, you have a hard time making a determination about whether the result is good or not. This is like the example where LLMs can hallucinate, right? You have to have some understanding about what's going on and in order to be able to make these decisions, right? It's like, how do you choose which algorithm, right? You can't iterate forever. You only have so much people and computational resources, and you need to talk about just diminishing returns. So here's the lesson somebody taught me at Google is, if you get 60 or 70% of your result with 20% of your effort, is it better to expend the rest of your effort to get 100% of one result? Or is it better to do 5 things and get 300% of, right? I think it's better to do 5 things and get 300%. So don't chase perfection. There's a point in diminishing returns, right? Sometimes it's good enough, it's better, right? We didn't have anything before. This is pretty good. And then, we can go on from there. Okay. So data splitting, right? Before you train, the data split to make sure that your model, I'm going way too deep in these. I'm sorry, guys. Before training, why do you split, right? You want to avoid memorizing the training data, which is called overfitting. We gave some of these numbers before, right? Training set is 70-80% to teach, validation is 10 or 15, and test is 10 or 15, right? And that's unbiased evaluation. And we'll be doing this live in some of our labs, so you'll see how this works. All right. So training, right? You learn patterns. Your goal is to optimize the parameters. And a model optimizes its own parameters, and you tune hyperparameters. Remember that, right? Model tunes parameters, but you tune hyperparameters. And those are the switches. It's going to tell you what features are most important. And the goal is to have less errors, works on data it hasn't seen before, and it's not just memorizing training examples, right? So it's like studying, reading a textbook and practicing problems. It's gradually you build understanding. Pretty soon you don't need your cheat sheet to understand what all the terms of machine learning mean, right? And then it's like you're getting ready for the real test. If you've ever done like a certification cram course where you take a bunch of tests over and over again until you get the answers and you understand that's kind of what this is doing. And then we're gonna have to figure out, we trained it, how do we know that it worked? Right? So validation is the practice test, right? So we're gonna use a trained model on a validation set. And this is the practice exam where the student takes the test to identify the weak areas, right? And then you go back and study. And then you go back and study more and more until you get the right answers, right? So you think about it, if you've ever taken a certification exam, you take practice exams. So that helps you figure out where you have gaps in your knowledge and where you need to go study more. Then testing is where we use that last little bit of data and we go through and we see if we get results that that are consistent with our testing and training, right? This is only used once, and you want to make sure that you have an honest estimate of real world performance and a true measure of the quality, right? How well does this work in practice? And it confirms that your model is ready to use. This is the final exam, I guess, for lack of a better term, right? And it shows you what actually was learned. And you do this one time. You don't get to validate or test again, sorry. So you never reuse your test set. Biases your results. And you don't modify a model based on test performance. You go back with your training data and validation data and adjust hyperparameters, and then you get new test data and test it again. Okay. All right, almost there, guys. All right. So then, real super briefly, we got Python for ML, which is scikit-learn. Check this out if you've never used scikit-learn before. Go and there's a ton of stuff out on the web about this. This is easy because it gets everything in one place. It's maintained. It's built on well-known libraries, and it's popular because it's got a user-friendly API for the different components and great documentation, and it's really used widely in industry and academics everywhere. I mean, almost everybody uses scikit, right? And then if you're going to scale to like cloud scale, then you have different options for some of these things. We talked about algorithms, right? All the algorithms that we discovered are contained in scikit. So we've got classification, regression, clustering, dimensionality reduction, and workflow support helps us to we'll learn how to choose the best algorithm, pre-processing, evaluation, and all this other stuff. I would ask for show of hands, but we're over as far as who's used scikit before. But if you have, you know how cool it is. All right. So how does this connect to the course? We're going to set up a Jupyter Notebook, right? And then we're going to be using this to actually do stuff with scikit as we go along. And it's the foundation for your capstone project. So everything is built around scikit. It's used by major security companies, right? The people that are building the black boxes are probably starting with scikit. And then it's scalable. It can handle large data sets, and the interpretable results is it can provide feature importance and model explanations. And we'll talk about that as we go along. Okay. All right. Key takeaways. All right. ML, you have supervised and unsupervised learning. You have algorithms. We'll learn about these more and more, right? Linear and logistics, decision trees, forests, and k-means solve different problems. We have a workflow, right? We got to split our data. We got to have training data, validation, and testing data. Never use our testing data again. And then scikit is your go-to Python library for implementing these concepts. And then that's all I got. Sorry. Hour and a half of 45 minutes of instruction. All right, I'm sure there's questions. I know we're over. Everybody's probably brain dead. Next class, we're gonna apply ML to practical examples, and then we're gonna on your own explore the scikit-learn documentation and try a simple ML project on a public data set. Do something, go and do classification of the iris data set. There's lots of great examples. Olufemi?
Yes, thank you. I was gonna ask about what category will you place ANNs and how do they perform against the other examples of learning type that you've mentioned in this class?
Are you talking about the algorithms?
ANNs, like artificial neural network.
Oh
Are
yeah,
they supervised or unsupervised?
yeah.
And how do
So,
they perform against?
well, it depends, and that's the performance tuning is a whole subject in and of itself, and that's where you get into things like hyperparameter tuning and stuff like that, and that helps you for each algorithm tune how well it performs, and we'll talk about that a little bit, but that's something. If you're interested in hyperparameter tuning, go ask your LLM about hyperparameter tuning. You'll say, give me a summary of hyperparameter tuning for machine learning, and it'll probably give you a better description than I can. Alex.
Hey, Stephen. Thanks. So one of the questions I have three questions. The first one is, how do we address bias in feature selection? The second one is, I'm working on a small project, more of like a POC for network traffic logs, where I'm analyzing, packet size and bytes sent.
Yep.
And one of the things that I'm having problem with is with the features. Some of the features where they are highly correlated, and it's just giving me a hard time with the coefficients interpretations. So how do I address that? And yeah, go ahead.
That's where you use techniques like principal component analysis to do feature reduction, and it's basically you can go through, and we're gonna show some of these techniques in future labs, but basically what you want to go through is have the ML algorithm determine feature importance, and it will help handle some of that correlation as well. And sometimes where you have highly correlated features, you might have to do feature engineering and add in another feature. And we can dive a little bit deeper into that as we go.
Okay, thank you. And last one, are we going to use TensorFlow?
Yeah,
in this course?
yep, we actually have a TensorFlow example where we're going to use TensorFlow and NLTK to talk about adversarial machine learning. So
Perfect. Thank you.
Yeah, you bet. All right, last question, or actually two last questions. Swayam?
Yeah, hi. I just have a general question about the assignment for setting up Jupyter Notebook. So when I was going through the document and all, and it said like I have to document like on a separate doc, like the
Yep.
setup process, and then once I go to Jupyter Notebook, I have to do another documentation for that. Do I have to put both of the set documentations in one doc, or like one in Google Docs or Word, and then one on the Jupyter Notebook?
What I was thinking more is you do the work in the Jupyter Notebook, and then you export. You can either cut and paste or export their Jupyter Notebook as a PDF, and then pull a piece.
Oh, okay. Okay, so just like I just transfer my Google Doc documentations into Jupyter Notebook and just turn that in.
Yeah, actually, vice versa. You take your Jupyter Notebook, you can put that in a Google Doc and turn it in, but you can turn in your Jupyter Notebook too. I'm cool with that.
Okay. All right.
Yeah.
Thank you.
All right, cool. All right. Again, sorry we're over. I'll try and do better next time. I wasn't supposed to talk this much about all these topics, but I did, so my apologies. Next time I'll try and be more brief, but there's a lot of stuff to cover, so I appreciate the questions, and you know, if you got more questions as we're going, hit me up in Discord and, you know, I'll answer for you.